Hey, so continuing looking into what we call planar transformations from ideas we saw yesterday of when you have a transformation matrix multiplied by a matrix relating to the vertices of some two-dimensional shape. And I want to start with understanding reflections, but reflections at different angles. And so what's familiar is that these columns here represent points to the vertices of some triangle. But I want to think about what will the image be of this triangle after it's reflected in the line y equals the tan 30 of x. So first, a bit of a weird way potentially of showing it a line. The key part is really the 30 degrees. I'll make a quick visual that I will then erase. But if I just imagine what that reflection line looks like, the tangent of 30, I will say the tangent of 30 is exactly 1 over root 3. So I could imagine a slope of up 1 over root 3, up 1 over root 3. Or, most importantly, it's a line that has a 30-degree angle between the x-axis and the line. And so imagine in the end we have a mirror placed like that. How would our image reflect about it? Because until now we've generally just reflected along the x and y axes and maybe with inverses a bit. That's it. That's what this means. And so in the end, all that really matters is I'm reflecting along a 30-degree angle going through the origin. And so I can now apply this transformation matrix here that with a bit of practice is pretty easy to remember. This represents this reflection. And so let me just start by writing this down. So it starts with the cosine of not 30 degrees, but 2 times 30 degrees. So in this case, 60 degrees times the sine, again, of 2 times the angle, 60 degrees. Same sine of 60 down here, and then minus cosine of, in this case, 60 degrees. And again, whatever is the angle formed between the x-axis and the line, that is what we're doubling every time. So that's my transformation matrix, and I multiply that by this matrix here of my vertices. Right, so here's matrix T, here's matrix A, and I would just use your GDC, and you get, I'll write everything as 3 significant figures. The actual messy numbers aren't so important. It's how we get here that matters. All right, so same idea for the next one, but instead of being given the angle directly, I have the angle indirectly told me. It's y equals negative x. So let's think what that looks like. The line of y equals negative x. I'll make a quick little visual here. So that looks like roughly this. That's the line of y equals negative x. So what matters to us is what's this angle from here to here? Well, that's negative 45 degrees. And I could use, if I wasn't sure right away, I could use some trigonometry by picking some points, but I know that's negative 45. I could also use this, 315 degrees. I could also think in radians, but I prefer to go with negative 45. All right, so my transformation matrix then will be the cosine of negative 45 times 2, so negative 90 degrees. It'll be then the sine of negative 90 degrees in both these places, and then minus cosine of negative 90 degrees. Other options that I haven't mentioned yet, you can also look at this. That's 135 degrees. And so I could use that and double that. And again, what we'll notice is that the cosine of 270 degrees is the same as the cosine of negative 90. So it doesn't matter what we pick. You do what makes you happy. And then at this point, while I'm essentially done, I'll mention one more thing. Because all these values in my transformation matrix, all these elements, are all either 0, 1, or negative 1 or something. So I will just write that out. For example, the cosine of negative 90 is exactly 0. The sine of 90 is negative 1, which means my matrix is actually quite pleasant. And I feel like I copied something. Oh, there should be in my impatience, I copied this down wrong. There we go. That's it. In the end, I should get a nice clean numbers compared to last time. Negative 1 over 2, negative 1, and 2, 3. Again, that's the the coordinates of A prime, B prime, C prime. All right, so here I have a triangle. I think it's the exact same points as before. Yep. This time I want to visualize, I want to find the vertices of the image after it's been a vertical stretch parallel to the y-axis by a scale factor of 1/2. So what does that mean? Well, a vertical stretch means a stretch that's going either this way or this way. Depends if it's an expansion or a compression. And notice all these arrows I drew are vertical. They're parallel to the y-axis. So I think the most important part of this is it's a vertical stretch by a scale factor of 1/2. And one thing we saw in this lesson is that I can model that quite nicely with a simple matrix in which if it's a vertical stretch, the 1/2 goes here, and if my horizontal is not changing, there's just a 1 there. And these are all zeros. If I put the 1/2 right here, then this would be a horizontal stretch by a scale factor of 1/2. And if these are both 1/2, I'd have 2 transformations at once. But this is what the question asks, and I always listen to the question. And so at that point, this transformation matrix shows a vertical stretch by a scale factor of 1/2. Pretty nice, clean matrix. Show the rest. I'm getting kind of tired of copying down these numbers. And we should get this. And one thing to notice, especially if we use our GDC or did this all by hand, is that in the end, because I just had a vertical stretch, notice none of my x values actually changed. And all that happened to my y values is they were all multiplied by 1/2, all cut in half, which makes sense. So to be honest, once you really understand what this transformation looks like, you may not actually need to do any matrix multiplication to figure out where those points are. All right, next, other way around, I give you the coordinates of the image. We want to find the transformation matrix. Now, one thing you may be tempted to do, for example, if I call all of this A prime, which is a totally fine idea, and A we've seen before, you may be tempted to think back to last day where if we have a transformation matrix times A, and we know what A prime is, we could use matrix multiplication to isolate matrix T. And we would multiply both sides by the inverse. This would become the identity matrix. So you have just T isolated. T equals the image of A, which I have, times the inverse of A, which my GDC can find quite quickly. But if you actually try this, it won't work because this idea only works if A is a matrix that is a square matrix that we can find an inverse of. A, in this case, is a 2x3 matrix. It doesn't have a multiplicative inverse, and so you cannot do this. If you tried it on your GDC, it would give you an error at one point, namely because you can't find an inverse to it. So that won't work. So how do we do this? Well, let's write down my 2 matrices here. So A again, and then A prime. And so since we can't directly solve this like in other days, what we can do is notice, okay, these are my y coordinates. They are unchanged. Okay, so this is not a vertical transformation at all. My x coordinates are all being multiplied by -3, but just my x, which means this is a horizontal stretch by a scale factor of -3, which is all my x values are being stretched by 3 times more and then change sign, so also reflect it. So now I can just go straight to my transformation matrix. That means the transformation matrix must be of the form like up here, except this was a vertical stretch. Now I have a horizontal stretch. I know the scale factor is -3. I know there is no vertical stretch, and so it must be this diagonal matrix. All right, last one. I have a simple triangle here, and I want to say it's being enlarged by this transformation matrix. 1.5, 0, 0, 1.5. All right, well, this is both a horizontal and a vertical expansion by a scale factor of 1.5. So you could just multiply, you could multiply this by the new matrix of A, B, C. Or, I think it's faster since I'm asking us to draw it anyways, is just realize this is, again, both a horizontal and a vertical stretch by a scale factor of 1.5 or 3/2. And so that means all my x values and my y values I multiply by 1.5. And so if I look at A, it was at 1, 1, and now it's at 1.5, 1.5. So right there's A prime. B was at 3, 2, so now it's going to be at 4.5, 3. Again, multiply both the x and the y by 1.5. And finally, C was at 2, 1, so now it's at 3, 1.5. All right, and so grab my ruler. Oh, that's an eraser. Grab my ruler and a pen. All right, so there is my image, which is, again, an example of a horizontal and a vertical stretch by a scale factor of 1.5. So then I want to find the area of this new triangle. Well, let me look at the old triangle first. If I look at this old triangle, area, quite simply, is area of the base times the height. And so it's 1 times 1, and then we divide by 2. So lo and behold, this has an area of 1 square unit. This here, area of the base is 1.5. Length of the base. The height, someone is calling me right now. My phone is vibrating. I apologize. It's spam. Maybe I should just pick it up and record. Nope. Okay. So area of this triangle is 1.5 times 1.5. Divide by 2 is 1.25. And so the area of this triangle, area of A, B, C, is exactly 1.25. Most importantly is, compared to before, this area here is, the shape is 1.5 times wider and 1.5 times higher. So overall, the area is 1.5 times 1.5, or 1.5 squared times more. And this idea will pop up in future lessons. And so in general, if I just have, instead of 1.5, a k, then the area of the new matrix, I just realized I made a mistake. You probably realize it. You're probably not even watching right now. You're probably wondering who I'm talking to. I wonder who I'm talking to as well. Sometimes I wonder if I should just get AI to do all this. Sometimes I wonder if I'm just going crazy. Anyways, I realized the area of this triangle is not 1. It's 1 divided by 2, so it's a half. All right, so that's it. This is still correct. I just made another mistake. I blame that person calling me. Anyways, so lastly, if I had this, then the original area was a half. That was the area of the smaller triangle. And if it's both a horizontal and a vertical stretch by a scale factor of k, the new area will just be k squared. That took way longer than it should have. Anyways, if you're still listening, thank you.